Hello everyone. Today I will explain how to calculate the median severity from a set of complaints whose severity values are grouped into ranges. Since the data is bind, we use the grouped median formula to estimate the central tendency. So here we are given with the data. We have severity ranges along with their frequencies. Some ranges have high counts, especially the 51 to 80 range with 1500 cases. And our goal is to find the severity level that splits the total number of complaints into two equal halves. So first we add up all frequencies. So the total count comes out to 2997 complaints. So the median position will be 9 by 2, which is 1498.5. Then to identify the median class, we now use cumulative frequencies to find where the 149.98.5 observation lies. So by adding frequency range wise, we see that the cumulative frequency crosses the halfway mark in the 51.51 to 80 severity range. Therefore, this range is our median class. Now, applying the median formula, here median formula is given over here where L is the lower boundary of median class, which is 51, and 753 also given, F 1500 and H 29, which is frequency of median class and class width. So by substituting, we get approximately 65.4. And so the approximate median severity value of the complaint is 65.4. So this tells us half of the complaints have severity below 65.4 and half are above it. So this helps in understanding the typical severity level in the data set. Thank you. Hello everyone. Today I will be analyzing a district intake sample of 18 complaints. We will compute the mean, median and standard deviation for both age and impact percentage. And then we will visualize them using box plots, scatter plots and quantile plots. So this table shows the age of each complaint along with the self-assessed impact of the incident in percentage terms. Both variables have 18 observations, so paired analysis is possible. We see the mean for age. The sum of all 18 ages is 737. So the mean age is 737 divided by 18, that is approximately 40.94 years. Then median for age for 18 values, the median is the average of the 9th and 10th values in sorted order. So the 9th value is 50 and the 10th is 52. So median will be 50 plus 52 divided by 2, that is 51 years. Now we calculate the standard deviation. Standard deviation measures spread. So using the formula of sample variance, the standard deviation comes out to approximately 13.07. So this shows the ages vary quite widely around the mean. Next, we see the impact percentage of mean. Now looking at the impact percentage values, their total is 459.1. Mean will be 459.1 divided by 18, that is 25.51 percentage. Then we see the impact percentage of median, again taking a 9th and 10th values 31.2 and 33.4. On calculating it, 31.2 plus 33.4 divided by 2, we will get 32.3 percentage. And standard deviation, using the standard deviation formula, the spread of impact values is about 10.36. So the impact percentages are moderately variable. Now we see the age box plot. The box plot for age shows mean is 23, minimum is 23, and Q1 is 27, median is 51, Q3 is 57, and maximum is 61. So this indicates that 50% of the ages lie between 27 and 57 with a long tail on the younger side. Then we see the impact percentage on box plot. For impact percentage, the 5 number summary is minimum is 7.8, Q1 is 25.9, median is 32.3, Q3 is 35.7, and maximum is 42.5. So this shows a compact distribution with most values between 26% and 36%. After that, we see the scatter plot between ages and impact percentage. That is here each point represent one complaint. So the plot suggests no linear correlation between age and impact percentage. The points are scattered randomly, meaning age does not predict perceived incident impact. So to summarize, age mean is 41, median is 51, and standard deviation is approximately to 13, and the impact percentage mean is 25.5 percentage, median is 32.3 percentage, and standard deviation is 10.36. Box plots confirmed the spread, and scatter plot as shown over here in the current slide showed no strong relationship. That's it. Thank you. Hello everyone. Today I will be explaining you the internal one solutions part B, question number 5, where I'll be explaining how we compute dissimilarity between students' feedback profiles when the data contains different type of attributes. That each attribute type requires a different distance or dissimilarity measure. So dissimilarity helps us understand how similar or different two student feedback patterns are, and this is important in clustering, grouping feedback, or identifying patterns in student experiences. So let's start with the nominal attributes part A. The comparison is very simple. Now the two students have the same category, dissimilarity is 0, and if they belong to the different categories, so the dissimilarity is 1. So we do this for each nominal attribute and then average the results. This is sometimes called the simple matching dissimilarity. After that, we see the part B, which is asymmetric binary attributes. For like symmetric binary attributes, the 1 value is more important than the 0. For example, attended is meaningful while not attended is not. So we use a Jaccard dissimilarity where only the cases where both have one matter. Matching zeros are ignored. So this gives a more realistic measure when one outcome carries more weight. After that, numeric attributes. For numeric attributes, we usually compute distance based on the actual values. The two most common formulas are Euclidean distance, straight line distance between two values, and second, Manhattan distance, that is sum of absolute differences. But before calculating, we normalize the values so that attributes like CGPA and attendance don't dominate just because they have different scales. Then we see the term frequency vectors, which is the last part. For open text feedback, we convert each student's response into a term frequency vector. That is basically a list of how many times each keyword appears. Then we compute dissimilarity using cosine distance, which measures the angle between the two text vectors. First is if the angle is small, then the responses are similar. If it is large, the responses are very different. So cosine distance works great for text because it focuses on the pattern of words rather than raw counts. Lastly, to summarize, nominal, which is simple matching 0 if same and 1 if different. Asymmetric binary, Jaccard dissimilarity. Numeric, normalized Euclidean or Manhattan distance. And text, that is TF vectors, which is cosine distance. Using the right measure, it ensures our analysis is accurate and meaningful. Thank you. Hello everyone. Today I will be explaining internal one solutions part B, question number 6. So today I'll explain how to calculate 4 different distance measures between two interaction profiles represented as multi-attribute tuples. So here are the given profiles P and Q. We have two students. Their interaction profiles include hours of monitoring, project reviews attended, assignment submitted, and infrastructure usage count. So first we compute the absolute differences for each attribute. Differences is 2, 1, 6, 2. So we start by Euclidean distance. Formula is given over here. So Euclidean distance is the straight line distance. We square each difference and add them. So 4 plus 1 plus 36 plus 4 is equals to 45. So then take the square root. Then the equilibrium distance is root 45, that is somewhat 6.7078. Then we see the Manhattan distance. Formula is given over here. Summation of xi minus yi Manhattan distance adds the absolute differences. So 2 plus 1 plus 3 plus 6 plus 2, that is 11. So the Manhattan distance is 11. Then we see the Minsky distance, that is h is equals to 3. Formula is given over here. For Minsky with power 3, we cube each differences. 8 plus 1 plus 216 plus 8 is equals to 233. Now taking the cube root gives us 6.15. And then lastly, we see the supremum distance, that is formula given over here. The distance is simply takes the largest individual difference and the maximum difference is 6. So the supremum distance is 6. Here are the all the distances. Euclidean is 6.7, Manhattan is 11, Minsky is 6.17 or 15, and supremum is 6. So these matrices help us understand similarity between students based on multi-attribute interaction data. Thank you. Hello everyone. Today I will be explaining the internal 1 part B question number 7. We will discuss efficient ways to approximate the median in massive or streaming datasets like student feedback scores where exact computation may be costly or impractical. So here median is a robust central tendency measure, especially for skewed feedback data. But when the dataset is huge or streaming, standard exact methods like sorting are inefficient. So we need algorithms that balance accuracy, memory, and speed. One practical approach is maintaining two heaps, a maximum heap for the lower half of elements and the minimum heap for the upper half. So insertion is O log n per element and median retrieval is O1, memory is On if we store all elements. This works well for online streaming median when we use where we can store all data in memory. And the second is reservoir sampling plus exact median on sample. For very large streams, we can randomly sample a subset of elements using reservoir sample. And we compute the exact median on the sample, and the sample size k is, for example, 10,000. Cost is on to sample plus o k log k to sort, and the accuracy is probabilistic, that is larger k improves confidence. This is a heuristic approach uh, when small probabilistic error is acceptable. After that, approximate quantile algorithms. This deterministic algorithms like Greenwald's Khanna gives approximate quantiles with fixed memory and are stream friendly. Other popular methods are QDigest and TDigest, which are mergeable, efficient, and very good for extreme quantiles. Then update cost is amortized. Then memory usage is there and small and controllable. These algorithms allow tight error guarantees even for large data. And then we see the another method, histogram or binding approach, which is maintained with a fixed width binds and count elements in each bin. So here median is approximated by walking the cumulative counts, and space is number of bins B, and the update cost is O1 per element. And accuracy depends on bin width. This method is very fast and simple for bounded numeric data. Then we see lastly distributed or the map reduce approach. In this distributed system, we compute local summaries or quantile sketches on each partition and then merge them. So algorithms like JK or TDigest are mergeable, or complexity linear total work across nodes, minimal network overhead, and this enables scalable median approximation for very large data sets stored across multiple machines. And at last, exact summary is that exact methods are accurate but costly in memory and time. But approximate or streaming algorithms offer trade-offs like two heaps, accurate and stores all data. Sampling is fast and probabilistic errors. T-digest and JK are small memory, mergeable, and guaranteed error. And histograms are simple, fast, and adjustable accuracy. So by choosing the method depends on data size and and streaming requirements and acceptable errors. Thank you. Hello everyone. Today I will be explaining you the internal 1 part B question number 8. So here we will see the rank existing students feedback profiles based on their similarity to a new feedback query using different distance and similarity measures. Here the data set is given over here. We have 5 students each represented as 2D vector. A1 is the faculty responsiveness, A2 is the infrastructure support. So student S1, S2, S3, S4, S5 are given over here, and A1, A2 their data set is also given, and the new feedback query is x is equals to 1.4 and 1.6. So the task A is the distance measured. We compute the similarity between each student vector and x using Euclidean distance, Manhattan distance, supremum distance, cosine similarity. All the formulas are given over here, and this lets us rank student based on closeness to the new feedback. So for example, step by step calculation, we see the similarity. For the Euclidean distance, we compute for all students and ranks by smallest distance, that is most similar first. So the calculation is done over here, and then we see the Manhattan distance for S1. Manhattan, that is 1 point mod of 1.5 minus 1.4 plus mod of 1.7 minus 1.6, that is 0.2, and the maximum mod of 1.5 minus 1.4 and 1.7 minus 1.6 is given 0.1. So repeat for all students to get rankings, and the observation is different matrices may produce slightly different ranking orders. Then we see the cosine. This is the supremum calculation. We see this cosine similarity. Cosine similarity measures the angle between vectors. Cos theta is equals to x multiplied by si divided mod of x into mod of si. So the for S1 dot product is 4.66 norms mod of x, and that is 2.2 for cosine similarity is also calculated here, and which is 0.98. It means that a higher cosine similarity will be gets the more similar. Then this all cosine similarity calculation is done for the S1, S2, S3 and S4, S5. Then we see the task B, which is normalization. Next, normalization means each student vector to unit length, that is SI normalized form. Then compute Euclidean distance to x normalized. This accounts for magnitude differences and focuses only on direction. So normalization often changes rankings slightly, especially if vectors differ in scale. So Euclidean distance between normalized vectors and x norm is also calculated over here. So in summary of observations, here it is that different similarity distance metrics emphasize different aspects: magnitude, direction, or max deviation. And Euclidean Manhattan focuses on absolute differences, and the cosine similarity focuses on purely on direction. And normalization removes scale effects, useful when attribute magnitude. Normalization removes scale effects and useful when attribute magnitudes vary. Thank you.